Hi friends, welcome to my another video. This is the part 9 video in series of designing of G+4 building as per DEWA regulation. If you remember, in part 8 video I discussed about the concept behind designing the MDB. In this video we will use that part 8 MDB designing concept and we will design here one MDB. So let's start this video. In order to brush up, I told you 5 steps involved in order to design any MDB. The first step is to finalize the total connected load on the MDB. Then we have to calculate the demand factor. We have to determine the demand factor. The third step involves that based on the demand factor we have to calculate the demand load. The fourth step involved in designing of MDB is that based on the calculated demand load we have to select the transformer rating. Based on the transformer rating we have to calculate the incomer size of the MDB. So there are 5 steps involved in order to design one MDB. I will tell you one more point here. The MDB incomer rating is not dependent on the total connected load or on the total demand load. It is depend on the source rating. Based on the source rating we have to calculate the MDB incomer breaker rating. But of course indirectly the transformer rating calculation depend on the total connected load and the demand load and on the demand factor. But if someone will ask that MDB incomer rating depend on which factor, how we are selecting the MDB incomer rating, then we are selecting the MDB by considering the source rating which is connected to the MDB. But of course indirectly it is depending on the total connected load and demand load, as the transformer rating it depends on total connected load and the demand load. I hope you are clear so far. This already I discussed in very deep in part 8 video. If you already followed my video from part 1 to part 8 in series of G+4 building designing as per DEWA regulation, then you already know how to design the final distribution board, how to design the sub-main distribution board, and apart from that how to distribute the load in a particular space. This we already covered in part 1 to part 8 video. If you remember, this SMDB already we designed in part 6 or part 7 video in this series. We took a floor, okay, and that floor have 6 single bedroom apartment and 1 double bedroom apartment, and based on this consideration we calculated and designed the SMDB. So if you remember, then you will find that the single bedroom flats are typical to each other electrically, and it has a total connected load of 14.9 kilowatt, 14.9 kilowatt, 14.9 kilowatt, 14.9 kilowatt, 14.9 kilowatt and 14.9 kilowatt. So total 6 flats of 1 bedroom and all have a same electrical load, that is 14.9 kilowatt. There is one 2 bedroom flat which having a total connected load of 18.75 kilowatt. Apart from that, we calculated the common area, light and power, and we make a load schedule for light dB and power dB. There is a little change from that design load for SMDB L1 common and DB P1 common. Here I took a load of 10 kilowatt and a total connected load of 12 kilowatt. Okay. So this SMDB already we designed. Based on using the same concept, we will distribute the load in a other area of that G+4 building and we will design the other SMDB. But here as the floor 1, 2, 3 and 4 are typical to each other, so the SMDB designing for L1 will be typical to L2, L3 and L4. Hope you are clear so far. Now, as we seen, if we will add all the load connected in the SMDB L1, we will get the total connected load. So we will do the same. The total connected load on SMDB L1 we will find. So the total connected load will be load on DB1, DB2, DB3, DB4, DB5, DB6, DB7, which are the flat DB, and the common light DB and common power DB. If we will calculate the all load, we will come to know that it is 130.5 kilowatt. Okay, so we need to know the current demand for this connected load of the SMDB. So what is the formula? P is equal to root 3 into V into cos phi. As we know that the total load on SMDB L1 is 130.15 kilowatt. So I mention here P is equal to 130.15 kilowatt. I change it kilowatt to watt, so I multiplied it with 1000. Then root 3 into V is 400 3 phase, and power factor I consider as 0.8. So based on the numerical calculation, we came to know that the total current required to satisfy 130.15 kilowatt of load is 234.8 ampere. So we know the current requirement for that SMDB L1. We have to select the incomer rating for that SMDB. So I consider the safety factor as 1.1. You can consider from 1 to 1.25. Any point in between, based on, as you are the designer, so you will decide this one. Okay, so I choose a value of 1.1 as a safety factor. So I will multiply this total current demanded on that SMDB1 with 1.5. Then we will come to know after calculation that it is 258.28 ampere. So we have to select the breaker rating. So the standard available breaker rating after 258.28 ampere is the 300 ampere breaker rating. So we selected the main incomer rating of SMDB is 300 ampere MCCB, and we discuss in parts 1 to part 8 video that there is a chart given in DEWA regulation for the breaker rating and the cable size. So we will refer that chart, and based on that chart we will decide the cable rating or cable size. But already I make a proper video on how to calculate the cable size for a particular load. As this topic is not that topic, so I will not cover all these points which I already discussed in one of my video, that is how to do the cable size calculation based on a particular load. Here I will refer a DEWA regulation which giving the relation between the breaker rating and the cable size. I will refer it, and based on that I will write the cable size. Okay, one more point, we will do the voltage drop calculation also for all our loads in upcoming video of this series, as the cable size depend on the voltage drop calculation also. If the voltage drop is more than 4% of the system voltage, then we have to go for the higher size of cable in order to reduce the voltage drop. Okay, but this will be a separate topic which will be covered in upcoming video of this series. As of now, consider that the selection of this cable will be having a voltage drop less than 4%. Okay, less than 4%. Now I will show you the DEWA chart where it is mentioned that which cable size we will use for 300 ampere MCCB breaker. Here you see this chart is for multi-core cables. This chart is for multi-core cables, okay, multi-core cables. As our selected MCCB rating or breaker rating, MCCB rating, breaker rating is 300 ampere. So the corresponding cable size is 185 square mm. But based on the voltage drop calculation, I selected a cable size of next upper size, that is 240 square mm. This I will show you in next video how I decided to go not for 185 square mm but to 240 square mm. But based on the DEWA chart, you can select the cable size based on the ampere rating of MCCB. So here you see for 300 ampere breaker, the cable size is minimum required is 185, but we can go for 240 and 300 square mm also. Okay, so this chart you take the screenshot, and based on this chart we will calculate the other SMDB cable rating or sizes. Okay. So I selected by considering the voltage drop calculation 240 square mm cable, and as we know that the earthing cable will be half of the phase cable, so 240 divided by 2, that is 120 square mm cable. Hope you are clear now. So this point I reflected here. The incomer rating of the SMDB L1 is 300 square mm and the cable size is 240 square mm. Okay, and the MCCB rating is 300 ampere. Hope you are clear so far. And you know, here I mentioned the cable size for the particular individual load. This I already covered in part 1 to part 8 video. Watch that video, you will come to know each and every point. Now same way I use the concept and I design the SMDB GR1. This have external DB, this have ground floor light DB, this SMDB have ground floor power DB, this SMDB have DB GR1, DB GR2, DB GRT3, and we have one MCBU which is of 5 kilowatt. So I know the total connected load of each DBs. Okay, I will calculate the total connected load of each load connected with the SMDB. Then we will come to know the total connected load on the SMDB. So let's start this one. So the total connected load on SMDB GR1 will be the load on DB external, DB GR1, DB GRP, DB GR2, DB GR3 and MCBU. So I wrote the corresponding loads of each DBs. After calculation we came to know that the total connected load on SMDB GR1 is 125.53 kilowatt, which I mention here. The total connected load on SMDB GR1 is 125.5 kilowatt. Based on the total connected load on SMDB GR1, I will calculate the current requirement for that MDB. So we will use this formula, P is equal to √3 into V into I into cos phi. So after putting all the numerical value, we will get the current requirement, current demand on the SMDB GR1 is 226.5 ampere. Again I chooses the 1.1 as a breaker safety factor. Then we will multiply it 226 with 1.1, then we will get a value of 249.1 ampere. So the next available standard rating for MCCB is 250 ampere. So I selected a breaker rating for SMDB GR1 is 250 ampere. Again, I will refer the DEWA regulation, and we find that for 250 ampere breaker rating, the cable size requirement is 150 square mm. From where I got this one? This is from the same chart of DEWA regulation. But here I'll show you once again that chart. Yes, here you see our calculated breaker rating came as 250 ampere. So 250 ampere, the cable size is 150 square mm. Here you will say why you didn't choose 185 next higher rating, because MDB and this SMDB are in the same floor. As we know, the MDB will always be in the ground floor, and this SMDB is SMDB GR1, so it will be also in ground floor. So the length of the cable is shorter, like 20 meter, 15 meter. This I will cover in next video. But based on the length of the cable, the voltage drop differs. So here the length of the cable is shorter, so the voltage drop will be also very small. That is why I choose 150 square mm cable. In same way, I have one SMDB in the roof floor which having a name SMDB LRF. Okay, and the loads connected are lift, BMUs, FHU, condensing unit, VRF units, lift 2 and GEAF exhaust fan. Okay, so these are the load connected with roof SMDB. So you can use the older concept and you can design SMDB LRF also. So what I will do, I will find the total connected load on SMDB LRF. So what I will do, I will add up all the loads connected with the SMDB LRF. So load on lift 1, BMUs 1, 2, 3, FHU, condensing unit, VRF units 19A, 19B and lifts. So after adding all this value, we got to know that the total connected load on that SMDB LRF is 179.50 kilowatt, which I mention here, 179.50 kilowatt. Now we will try to calculate the total current requirement for that SMDB LRF when the total connected load is 179.50 kilowatt. So I will use the same formula. I is equal to P divided by root 3 into V into cos pi. As we know the P, the total load on the SMDB is 179.50. We'll put all in the numerical value. We will get the total current demand on SMDB LRF is 323.8 ampere. I took the safety factor as 1.1. So I calculated the calculated breaker rating as 356.2 ampere. The next available breaker rating is 400 ampere. 400 ampere. So based on the breaker rating, I again refer the DEWA regulation and I selected the cable rating as 300 square mm with the earthing cable, half of it, that is 150 square mm. Okay. Now we have another SMDB which is also in ground floor. So I will repeat the same process. Okay. We will find the total connected load on SMDB GR2 which came as 94 kilowatt. Then again we will calculate the current requirement on SMDB GR2 which came as 169.6 ampere. Okay, we will multiply it with the breaker safety factor, that is 1.1. then we will get the calculated current as 186.5 ampere. The next available breaker standard rating is 200 ampere. So Based on the breaker rating, we refer DEWA regulation and we calculated the cable size, that is 95 square mm, and half of its earthing cable, that is 50 square mm. Now I will show you in DEWA regulation what is the cable size for 200 ampere breaker rating MCB and for 400 ampere breaker rating. So as I mentioned here, for 400 ampere MCCB, the cable size is 300 square mm, and for 200 ampere MCCB, the cable rating, the cable size is 95 square mm. So I will show you. This chart is for multi-core cable and this chart is for this chart is for PVC insulated multi-core and this chart is for XLP insulated. So our cable is XLP insulated, so we will refer this chart. Okay, for 200 ampere MCCB, the cable size is 95 square mm, and for 400 MCCB rating, the cable size is 300 square mm. Hope you are clear so far. Now we have to summarize the load on the MDB, which is step 1. We have to summarize the total connected load on the MDB. So what we will do, we have SMDB GR1, SMDB GR2, 4 typical SMDB, that is SMDB L1, SMDB L2, SMDB L3 and SMDB L4, and we have one roof DB, and we have one DB which is feeding the substation, and we have one firefighting panel, firefighting electrical pump, which is having a total load of 125 kilowatt. So we have to summarize the total connected load on the MDB. Okay, so what we will do, we will add the load on SMDB GR1, SMDB GR2, L1, SMDB L2, SMDB L3, SMDB L4 and SMDB LRF plus DBTR and the total rating of the fire pump. So once we will calculate all the load, we will get that the total connected load on the MDB is 1037.21 kilowatt. This is the step 1. As I told you, finalize the total load on MDB. So we completed the first step, that is the total load on MDB is 1037.21 kilowatt. Now step 2 is to determine the demand factor. This I will cover in part 11 video after, because in part 10 video I will cover the voltage drop calculation. In part 11 video I will cover the how to determine the demand factor, which is itself a very lengthy topic. So time being, assume that we calculated the demand factor as 0.792. So the second step is completed, that to determine the demand factor. We determine the demand factor, that is 0.792. Based on the demand factor, we have to calculate the total demand load. So what is the formula? The formula is, to calculate the demand load, is total connected load into demand factor. Okay, so I multiply total connected load with demand factor. So we got the demand load as 821.5 kilowatt. Okay, so we completed step 3 also, that now we know the total demand load on the MDB, that is 821.5 kilowatt. Okay, now what is the step 4? Based on the demand load, we have to calculate the transformer rating. In the part 8 video I discussed these 2 points in very detail, but I will brief you here. As per DEWA regulation, when the load, it's not mentioned total connected load or demand load, when the load on the MDB is 401 to 800 kilowatt, okay, then we have to go for a transformer of 1000 kVA, and the incomer rating of MCB for the MDB should be 1600 ampere. For a load on the MDB is 800 to 1 kilowatt to 1200 kilowatt, okay, then the transformer rating will be 1500 kVA and the air circuit breaker rating will be 2500 ampere. Here you will ask why you are not saying it is which load. Suppose I consider the demand factor as 1. Then in this case my total connected load is equal to demand load, because I will multiply it 1 here, so it will be same. Okay, so this demand load, when we consider the demand factor is 1, is not a total connected load, it is a demand load. Though the demand factor is 1, in that case the demand load will become equal to total connected load. Okay, hope you are clear. So what is the point here? This is the demand load or total connected load, no need to worry about, because the total connected load and demand load could be equal to each other when there is a demand factor equal to 1. So you are the designer, you have to design the MDB based on the demand factor. So if you consider the demand factor as 0.85, okay, so whatever load came after multiplying total connected load with the demand factor, that load you have to consider here, it is in between this range or in between this range. Based on that you have to select the transformer rating. Okay, so in all cases, for in a simplicity, in all cases you have to go for the demand load. Okay, so here now our demand load is 821.5 kilowatt, which is in between this range, 801 to 1200 kilowatt. So what would be the transformer size? The transformer size will be 1500 kVA. So now we calculated the transformer rating as 1500 kVA. Based on the transformer rating, we have to select the breaker rating of MDB, that is, as per DEWA regulation, it is 2500 ampere. So we selected as per the total demand load, that is 821.5 kilowatt at demand factor 0.79. The transformer rating is 1500 kVA and the incomer rating of MDB as 2500 ampere. So this I reflected here. The total connected load 1037.21 kilowatt, demand factor here is 0.792, total demand load 821.5 kilowatt. Okay, so this I mention here. And what is the breaker rating, which I mention here, that is 2500 ampere triple pole MC ACB. Now this is the SLD for the main distribution board. Here I mentioned SMDB 1 and its corresponding total connected load and its cable, that is 4 core 150 square mm, which we calculated in this video. Same for SMDB 2 and its total connected load and the cable size for SMDB GR2. Apart from that, we write the corresponding breaker rating also. For example, I'll tell you, SMDB L1, L2, L3 and L4 have a breaker rating of 300 ampere. The cable rating of 240 square mm. Okay, so let's see. Just what we calculated, we are reflecting here. Okay, so we'll see one of the example. This is SMDB L1. Okay, the incomer rating is 300, which I reflected there, and the cable rating is 240 square mm, which I also reflected in the MDB. And the total connected load, that is 130.15 kilowatt. The same thing I reflected in the MDB. Here you see the total connected load 130.15 kilowatt. Here the breaker rating 300 ampere, the cable rating 240 square mm. For say in same way we will write for all our SMDBs. Here for SMDB DBTR, it is a single phase. Why it is single phase? Because the total connected load is less than 10 kilowatt. So it is a single phase, which I already discussed in part 8 video. The breaker rating is 32. And here we have the total connected load for the fire pump is 125 kilowatt, and corresponding breaker rating is 300 ampere. In part 8 video, I told you about one point which is very important. As any load, any individual load more than 100 kilowatt in a particular MDB, then we can use 1000 kVA transformer for a total connected load of 650 kilowatt, and we can use 1500 kVA transformer for a total connected load of 950 kilowatt. But suppose on a SMDB all individual load are less than 100 kilowatt, then what is the case? We can go 1000 kVA transformer for a total connected load between 401 to 800 kilowatt, and we can go for 1500 kVA transformer for a total connected load in between 801 to 1200 kilowatt. But if in case any of the load on the MDB is greater than 100 kilowatt, then this situation is not true. We can go till 650 kilowatt for 1000 kVA and 950 kilowatt for 1500 kVA. But in our case we have one individual load which having a rating more than 125 kilowatt. Then why we did not apply that the second case? Here there is one question. That load, as I told you, 100 kilowatt greater individual load, then we have to go for 1500 kVA transformer for the total connected load of 950 kilowatt, right? Here when the fire pumps starts, when there is a fire in the building and all the HVAC loads are integrated with the fire alarm, that is when the fire activated, the HVAC loads get shut down. The fresh air loads, AC loads, all will get shut down, right? Because all the DB or AHU directly, FAHU directly will be interfaced with the fire alarm. As the fire alarm activated, these all services will be closed. So the total connected load on the building during fire condition will be very less. So if this 125 kilowatt of fire pump will start at this situation, it will not be harmful for the transformer. Here might be you confused that here the SMDB load is greater than 100 kilowatt. This SMDB also have greater than 100 kilowatt. This SMDB also have 100 kilowatt. This SMDB also have 100 kilowatt. Most of the all SMDB have 100 kilowatt except this SMDB. So why we are not choosing the transformer rating based on the second case, that is for 950 kilowatt connected load we have to go for 1500 kVA. Here this I already explained you in my previous video, but I will just brush up you. This SMDB total connected load is based on numerous load connected on the SMDB. For this SMDB also same, there are many load connected with this SMDB. So the individual load, any individual load in that SMDB is not exceeding 100 kilowatt, as the total load on SMDB is 130. So how come the individual load will be more than 100 kilowatt? For example, if you will consider, so you can refer that SMDB designing also. For example, here you see it is 12 watt, it is 5 watt, it is 5 watt, it is 5 kilowatt, it is 17 kilowatt, it is 47 kilowatt, 36 kilowatt, 36 kilowatt, 14 kilowatt and 0.5 kilowatt. For all SMDB you will refer. Here you will see that it is 8.7 kilowatt, 7.8 kilowatt, 20.2 kilowatt, 26.7 kilowatt, 31 kilowatt, 26 kilowatt. So all the load on the SMDB are less than 100 kilowatt. That, and the second point, as I told you, the fire pump will start during the fire condition, and at the fire condition most of the AC load will be shut down. That is why we can go for the first case, that is we can choose a 1500 kVA transformer for a load up to from 801 kilowatt to 1200 kilowatt. Hope you are clear so far. Now we, for the SMDB designing, we calculated everything except our capacitor bank. Okay, so let us consider and calculate the capacitor bank briefly, but we have already one video in part 1, part 2, part 3, part 4 regarding the capacitor bank size calculation. But in order to complete this topic, let us calculate the capacitor bank size calculation. We know the formula, that is Q is equal to P total connected load into tan actual minus tan desire. So we know the total connected load, here it's wrong, total connected load is 1037.21 kilowatt, right? Our actual power factor is 0.8 and we need to improve the power factor to 0.2, okay, 0.92. So we mentioned the total connected load, that is 1037.21 tan theta. If we know cos theta is equal to 0.8, then what is theta? Theta is equal to cos inverse 0.8. So which I mention here, in place of theta I mention cos inverse 0.8 and cos inverse 0.92. So when you will do the numerical calculation, you will get to know the kVAR rating for the capacitor. Calculated kVAR rating 336.05 kVAR. We have to always round up this value with multiplication of 25. So the next nearest multiplication of 25 will come as 350 kilowatt. Okay, so our total kVAR rating for the capacitor bank is 350 kVAR. We have to calculate the MCB rating for this capacitor. So we know Q is equal to root 3 into V into I into sine theta. We will consider sine 90, that is equal to 1. So here multiply by 1, which will not affect this numerical calculation. So based on, I will put all the value, then we will come to know I is equal to 505.2 ampere. Okay, so as per the I standard, if we are calculating any breaker rating for the capacitor bank, we have to multiply it with 1.3 into 1.1, which I already discussed in the capacitor bank series. Go and watch that video, you will get more information. So I will multiply it 1.3 into 1.1 into the calculated current, that is 505.2 ampere. So we will get the calculated MCCB rating as 721.4 ampere. The next available breaker rating is 800 ampere. So I selected here the breaker rating for the capacitor bank 800 ampere and the kVAR rating as 350 kVAR. I will discuss in any upcoming video about the ammeter, voltmeter, what is SPD, okay, what is the where we have to fix the CT, what is kWh meter, okay. These all we will discuss in any upcoming video of the MDB designing. I hope you find this video informative. If you really like this video, then please give thumbs up and subscribe to my channel. Please share this video with your electrical friends. We will meet in any other video. Till then, take care, keep learning, and bye bye. Thank you so much.